Alright, good evening guys, welcome to lecture 1.7 on unit 2, nuclear fission. Here are the learning intentions and success criteria for this chapter. Please pause the video and attempt to complete the KS table. Alright, so having a look here, we've got a couple of verbs: describe and explain, and there's a defined and the success criteria there. So this is all about knowledge about these things. So first thing we should know is, well, what is nuclear fission? If you don't know what it is, it's very hard to define it, and it's very hard to describe a particular type of it. The next one is we need to explain what is that neutron induced. So we need to know, well, what does neutron induced mean in the first place? So putting those together will help us do the second criteria there. And then finally, well, what is a chain reaction? If we know what fission is, we know what a chain reaction is, we'll be able to do step 3 and complete the entire learning intention there. So in the previous video, we looked at bombardment. We saw how nuclear bombardment causes artificial transmutation. We use this extensively in investigating creation of new elements. We'll talk about that in topic 3 when we look at the standard model. It's also of critical importance in the use of nuclear power. Now, we saw 4 types of bombardment. We saw proton bombardment, we saw neutron bombardment, we saw deuteron, and we saw alpha bombardment. And another way of using that would be, say, to proton induced, or alpha induced, or neutron induced. The other way of thinking about a nuclear equation is, what does the product do? Sometimes the products might undergo, also the reactants might undergo fusion to become something new, and they'll be more stable. Sometimes the product, the thing that is produced, will then undergo fission. And we're going to discuss fission in this video. We'll talk about fusion in the next one. So, neutron-induced fission is what the name describes. The word induced in this case means started by. So neutron-induced means we started with a neutron, like we saw in the previous video. A fission reaction, though, is a little bit more complex, and a fission reaction is where a daughter nucleus, and this is the definition from the syllabus, but a daughter nucleus produced splits into 2 or more smaller stable nuclei, which could be different elements, remember, as well as some smaller particles in the form of neutrons or protons, and some energy. So, let's have a look at that. I've rewritten it a little bit here. Where a nucleus produced by bombardment, because we have to trigger this thing first, and we trigger it from bombardment, splits into 2 or more smaller, more stable nuclei. Now this is different from just radioactive decay. So if we had just an atom of uranium-238, it would just decay over time, spit out a small bit, change what it is. If instead we were to hit it with a neutron, the change it would go through would be significantly different. We'll see that in a little bit. Often there's some free protons or neutrons, and there's some energy as well. Okay, so it has to split into 2 or more atoms that are, quite different from the original. It has some protons and neutrons as well. For fission, though, we're mostly looking at elements above iron 56. Now, we talked about that a little bit in the previous video when we looked at the binding energy per nucleon. We'll do a bit more with that in fusion when we compare the 2 types together. So we won't be talking about that too much in this video. So, let's think about neutron-induced fission. When scientists were first looking at what happened when you bombarded atoms, they found something weird with uranium-235. Sometimes it made things that were very small. And they found it would produce krypton-92 and barium-141. There are some other versions of the split, but those are the common ones. And also made some extra neutrons along with the energy. So here is the image for it. Here we have a neutron smashing into a uranium atom. I do apologize, it's a bit blurry from what I can see, so it is in your text though. So we have a neutron smashing into a uranium-235, and this one looks weird, and they're using this here to represent the fact that it's unstable. That unstable atom then turns and splits into some krypton, some barium, not the planet, it's an element, krypton, barium, 3 neutrons, and some energy. If we were to write this in an equation, it looks like this. 1 neutron plus uranium-235 produces uranium-236, which then produces krypton-92, barium-141, 3 neutrons and a gamma ray. Now, usually this bit here in the middle is not done. Normally they just go, yep, this plus this gives all of this. And if we were looking at the balancing of the equation, we would look, well, 1 plus 235 is 236, 92 plus 141 plus 3 times 1, because there are 3 neutrons here, you've got to be careful with that, will also equal to 236. Well, at least I should do if I've done the math right. Yeah, 231, yep, 236. But we normally wouldn't draw this bit here in the middle. I'm just sort of putting in here to show this in that format. Okay. Now the text has a really good description of how the atom actually does its split. Have a read through that. To me, it doesn't seem like it should be part of the syllabus in terms of the assessment, but it will help you understand why smacking a neutron into it causes this instability. Now if we have a look at this equation, we see that on one side we have 1 neutron going in, and this other side we have 3 neutrons coming out, and that's really, really important, because if we took these 3 neutrons and we had some more uranium nearby, then we could trigger more of this. Okay, so for every one of these that happens, we could trigger 3 more, and this is called a chain reaction. So here's the image from your text on this, and we see 1 neutron comes in, bang, a couple of smaller ones, and then we have some neutrons. Here they've actually said 1 neutron is lost, but these other 2 go on to hit. Split, 1 is lost, next 2 hit, 1, 2, 3, 4. Then you've got 1, 2, 3, 4, 5, 6, 7, 8 neutrons going on to hit. This is a chain reaction. 1 is producing 2, which produces 4, which produces 8. The neutrons event trigger more reactions in this continuous escalating fashion. Nuclear weapons use this idea, nuclear power plants use this with control, and a meltdown will happen like Chernobyl if this isn't controlled. Because each reaction releases neutrons, which are pretty nasty for us, but also gamma rays that can cause destruction, but it will heat up water to run generators, and so this can be used to power things. In the previous video I showed you about the mass defect for a single atom, but if we look at the mass defect for this nuclear equation, this one's using a different pair of elements, but if we looked at the mass defect for this equation, we will see the exact same phenomena we saw on a single atom. Okay, so let's have a look at that. Uranium-235 weighs 235.044, and 1 neutron weighs 1.009. The krypton mass is 91.926, barium 141, 140.91, and 3 neutrons weigh about this. Now if you add all these up, if you add these 2 and you add these 2, you get a difference of around close to 1 atomic mass unit. And so that energy has to go somewhere. All this product weighs less than this. It has less mass. We could use the exact same process we used on the previous one to work out how much energy that actually is coming off in that gamma ray. We would just add up the masses, take the difference, whatever that difference in mass is, turn it into kilograms, and feed it into E equals mc squared to work it out. So let's have a look at an example of this. Oh, the final, all these added up is about 234.858. Sorry, so it's about, yeah, it's pretty close to 1. About 1. Alright, so let's have a look at an example. So this is from your book. For the uranium fission reaction shown there, calculate the energy released in a couple of different ways. Joules per fission of an atom, that's the same as what we've done before, but then another version, joules per kilogram. Now, in terms of joules per fission, we need to know, well, what's the mass before and what's the mass afterwards. Now, all the isotopes that the textbook uses are in the back of the textbook, so refer to them there. On an exam, they would be provided to you in the work booklet or as a separate mass sheet, but it would not be information we expect you to memorize. Even the masses of the neutron and the protons, for example, they would not be expected for you to memorize them. You would be expected to use, though, to a fairly significant number of digits, because it's in this very small, fine detail that these things matter. So let's have a write. So I will write out the equation first. The equation that we are using, because it's a bit small, sorry, is uranium 235, and I'm just going to put the mass numbers plus a neutron gives us strontium 94 plus xenon 139 plus 3 neutrons, and there's some energy. So we need the masses of these bits, we need the masses of these bits. So the mass of uranium is equal to 235.043.930U. The mass of a neutron is equal to 1.008665, while the mass of strontium, so strontium 94, has a mass of 93.915356. Xenon 139 is 138.918792. So I should put the units on there. And finally 3 neutrons is just going to be 3 times that. You don't need, if you've got 3 neutrons coming off, they are all separate, so you don't have to go, oh well, is it some weird combined and I've got to know the binding energy for having 3 neutrons together. Now we just take the mass of 1 neutron multiplied by 3. So 3 times 1.008665. Now we add those ones up together on this side, we're going to get 236.052 595. We add up the masses on this side, we get 235.860143. And so we can see here the change in mass is going to be, the difference of this take away this, and so the change in mass, or the mass defect, remember, is equal to 192.452. I'm working off the worked example here. I don't have to do the math too much. Now, sometimes you will get where the mass initial and the mass final will actually be a negative number. That means you have to put some energy in. You can still use the E equals mc squared equation. However, you should just be aware that you need to deal with this. Generally we put the absolute value of the number, the positive value, into the equation so we get the energy. But the negative can be useful, so don't be worried if you get a negative. Okay, so now that we've got the amount of mass that's being released here, we need to turn this into what's what I'm looking for? Kilograms. So we're going to take the previous conversion we saw in the last video, where we now are going to multiply this by 1.66 times 10 to the negative 27. That is inside your formula booklet, so you don't have to memorize that number. So delta M is going to equal this 0.192452 times 1.6606 times 10 to the negative 27 equals 3.196 times 10 to the negative 28 kilograms. We're at the end, E equals mc square, so 3.196 times 10 to the negative 28 times 9 times 10 to the 16, that's the c squared, gives us a final value of 2.88 joules, times 10 to the negative 11 joules. Now, this one looks like it's got a fair amount of working. The amount of working on this really just comes down to, well, add up all the pieces afterwards, add up all the pieces before. The math itself in terms of the physics is fairly straightforward. It's just getting through this that is quite tedious. Okay, so we have here the amount of energy released from one atom. So that's part A of this question. Part B is asking, well, what's the joules per kilogram? We've got here joules, and I'll just put it here, per atom. So we now need to go, well, what is this in joules per kilogram? And we're going to need to know, well, how many atoms are in 1 kilogram. So if I know how many atoms are in 1 kilogram, and I know how much energy is released from one atom, then I can figure this out in terms of, what's the word I'm looking for? I can figure this out in terms of, well, how much this actually is. So, I'm going to, unfortunately, have to erase all this. So if you need any of the working, just pause, go back and copy down what you need to. This is a bit tedious, I do apologise. Unfortunately, not an easy way to get rid of these things so that I've got room to work. Probably should have made 2 pages, to be quite honest. And I'll just leave the energy value right down the bottom, because we are going to need it, I'm sure. But all the other working we don't. Okay. So, we know the energy per atom of uranium-235 is down there. We need to know the mass of, or how many atoms of uranium-235 are in 1 kilogram. So, the mass of uranium-235, after we put all the bits together, remember, is equal to 235.043. Should do the 930 as well. U, and we need to turn that into kilograms. So we're going to multiply that by 1.66 times 10 to the negative 27, because remember, the mass of one atom, or 1 AMU multiplied by this gives us how many kilograms, or that 1 AMU is this many kilograms. Multiply that together, we get, and there is an error in the text on this because they've forgotten the power, the negative power, 3.90 times 10 to the negative 25 kilograms. Okay, so that's the mass of one atom. Well, we want to know, well, how many atoms are in this thing? The way to work this out is if we take 1 kilogram and divide that by that, we'll know how many atoms go in it, because we're after really how many groups go into this. Divided by 3.90 times 10 to the negative 27 is equal to 2.56 times 10 to the 24 atoms. Okay, and now we've got the amount of atoms, and we know the amount of energy from one atom. We multiply these two together, and we've got the amount of energy per kilogram. So 2.56 times 10^24 multiplied by 2.88 times 10 to the negative 11, and we end up with an answer of around 7.38 times 10 to the 13 joules per kilogram. So if we have 1 kilogram of uranium and we were to decay this, because this is, remember, this is the energy per atom decayed, not the binding energy of the atom itself, but just the energy released from the decay, we end up seeing here that this is quite a lot of joules in 1 kilogram of energy. Okay, so in this video we have gone through the following. We have defined nuclear fission, we've explained a neutron-induced fission reaction where we smash a neutron in to cause a fission reaction, and then we've explained a fission chain reaction, and we've done some calculations with those, wherein we can go, well, if 1 causes 2, 2 causes 4, 4 causes 8, etc., etc. For interest of class, please have a look at chapter 6.2 and complete questions 2, 3, 5 and 6. Put those into the 2.1.7 space on eLearn. Thanks very much, guys. Have a great evening.